We're going to start with number theory, and we've been talking about factors and multiples as we've talked about multiplication and division. But
So
we'll
number
extend
theory is a
that
part of
idea in this
mathematics
section
that is devoted to the study
of non-zero whole numbers and how they relate to one another. And historically, numbers have always kind of fascinated people, and one of the carryovers is from that is the fact that some people are scared of the number 13 or they have fear of 13. In fact, in hotel rooms, hotel buildings, they don't even have a 13th floor. Okay. Or sometimes even a room 13 is just carried over so long. So, just like we've done with multiplication and addition, we want to be able to relate things together with models because, first of all, that helps children develop their own understanding of why numbers work the way they do. So, what we say is that one number is a factor of a second number, or we can also say that the number divides the second number. Being a factor and divides is synonymous. So we say 3 is a factor of 12. We also say 3 will divide 12. Okay, so if we have one number as a factor of another, then the second number is a multiple of the first. Okay, so we can say that 3 is a factor of 12, which is the same as saying 12 is a multiple of 3. So they have this inverse relationship to each other. So mathematically we would state this: if a and b are whole numbers and a is not 0, and we have to specify that a is not 0, because if I multiplied a and b together, one of them was 0, I'd get 0 answers. So if we do have these numbers, then we say a is a factor of b if and only if there's some whole number c that if I multiply it by that a, I'm going to get b. And the equivalent of saying that a is a factor of b is to say that a divides b. And if that's so, then b is a multiple of a. So we have different kinds of models. Okay, and one of them is a linear model. And usually we can illustrate this with a rod that would be 32 units long. And since I can take a rod that is 4 units long and put it together to make a rod of the same length, then I know that 4 is a factor of 32. Okay, so what I see here is that if I take these rods of length 4 and put 8 of them together, so 8 times 4, I'm going to get 32. So that both 8, the number of these I have, and 4 are both factors of 32. Another model which really relates to the area model of multiplication we were using with the base 10 models is a rectangular model. Okay, so in this model, if I have one side of a number representing one factor and then another representing a second factor, then I get the multiple by multiplying those two together. So it says here one way to determine whether a whole number k is a factor of some other whole number b is to try to build a rectangular array. So in the last one, if I wanted to see how many times 13 would go into 169, you could build a rectangular array that one side was 13 and then figure how many repetitions of that do you have to add together or put in an area model to be 169. So here, since I have this 7 and this 12, these two are the factors, and they're the dimensions in my area model. And when I multiply those two together, I get the number of unit squares, and that tells me what the product is. Okay, so I know the side lengths are both factors, and 84 is a multiple of those side lengths. So for a bit of notation here, okay, when I want to say that 12 is a factor of 84, which we've seen, I can also write that symbolically as 12, and the symbol means divides 84. So putting this in a symbolic definition, if a and b are whole numbers such that a divides b, which means a is a factor of b, then we write a divides b. This is not slanted, this is just an upright vertical line. Okay. If a doesn't divide b, if it doesn't go evenly into b, we just write doesn't divide. So divides here doesn't indicate we're doing an operation of division. What it says is just the relationship between the two numbers. One is a factor of another. So you wouldn't use this symbol for divides to indicate division. Okay, so it does not indicate the operation of division. So if I have 3 divides 15, that tells me not 3 divided by 15, it's not a fraction. It tells me that 3 divides 15, which means 3 goes evenly into 15. It's a factor of 15. So we don't want to confuse this notation, which is the relationship between this notation, which is an operation, division. So here are some other rectangular array models. Okay, so these are all for the number 16 in this column. Okay, so I could have a 16 by 1, I could have an 8 by 2, I could have a 4 by 4. Then I could rotate this 8 by 2 to get this one, and rotate this 16 by 1 to get this last model. Okay, so some of them are just pivoted rectangles with the same dimension. The first one and the last one, the 2 by 8 and the 8 by 2. And then of course the 4 by 4, if I were to pivot that, I just get the 4 by 4 backwards because it's a square. So we have this pattern that we're going to get to somewhere. Maybe we get a square, maybe we don't. But once we get past a certain place, then we start pivoting our rectangles, and we end up with the same two factors repeated. So here, where I'm looking at models for the number 30, okay, so the 1 times 30 is just a pivoting of the 30 times 1. The 2 by 15 is just a pivot of the 15 by 2. The 3 by 10 and the 10 by 3 are pivots of each other. And then the 5 by 6 and the 6 by 5 are just pivots of each other. Okay, so we see that once we get to a certain place, in fact for here, is once we get here, we start having the same factors repeated again. So first of all, the factors of the numbers occur in pairs, always, 2 for each rectangle, except where you have a square array, because you don't have 2 different factors, you have the factor 4 repeated, as in 16. So when I look at 16, if I look at all the dimensions of the different rectangles, that tells me what the different factors are of 16. And the same thing happens if I list all the different dimensions of the rectangles that made up areas with 30 as the product. Okay. And then the third observation is that we can see we know that the factors are occurring in pairs. We can see what the factors are by looking at the side lengths. And then we can see that after we get to a certain point, we start duplicating the same factors again. Okay, this happens at the square array for 16. And then for 30, it happened when we got to the 5 by 6 array, that when I pivoted it, I just got the 6 by 5 array. Okay. So again, right here was the pivot point. So then the factors begin to repeat when the rectangle is a square, or as close as it's going to get to a square. And that's important to remember. So from that figure, we have that square arrays or rectangles that are close to square arrays are the turning point, okay, for other factors. So that way, if I want to find all the factors of a number, all I have to worry about is getting the factors that get close to that square. So if you remember for the basic skills test, when we wanted to decide if a number was prime, if it had factors other than itself and 1, what we could do was take the square root of the number. So in this case, when I have 16, okay, then the square root is 4. All I have to do is look for factors of 16 that go up to 4. So I only have to test the numbers that are 1, 2, 3, or 4 to see if they're factors of 16. Okay, for 30, I only had to get to that 6 because I have, when I have that repeated square, a rectangle, a 5 by 6 and then a 6 by 5, okay, I want to include the 6. I don't want to skip it as one of the factors. Okay, and what I would find out is that if I squared 6, I get 36, which is close to 30. So what I have to do is check for the factors that are all 6 or less. Okay, because once I get to past 30, then I don't have to check anymore. So if going to 36 would give me enough room to check for all the prime factors. Okay, so if I'm looking at 188 and I want to find all the factors of 188, okay, now 188 is not a perfect square. I can't find a number which I multiply by itself to get 188. But I do know that if I take 13 multiply times itself, I get 169. And if I take 14 and multiply it by itself, I get 196. Okay, so this is just a little bit more, so I have to go to this point. So for all the rectangles for which 188 will be the area, then the dimensions have to be less than 14. I don't have to repeat going all the way up. So then if I check, I find that there's a rectangular array that's 1 by 188, a 2 by 94, and a 4 by 47. Since those are the only rectangular arrays, then each of these numbers, 1, 2, 4, 47, 94, and 188 are all factors of 188. Okay, so let's look at this number 11. Okay, we only have one model for the number 11, and it's a 1 by 11, or its pivot, but essentially one model. And then for 10, we have this model, a 1 by 10 and a 2 by 5. Okay, so we only have one array for 11 and two arrays for 10, and so our only factors for 11 are 1 and 11. And the factors we have for 10 are each of these: 1, 10, 2, and 5. So let's look at the array, what we could get for the numbers 1 to 9. And I believe this is part of your lab activity. So when I list all the factors of these numbers, I could draw their area representation, and I find out how many factors I have. Okay, if I have exactly 2 factors, like here and here and here and here, these numbers are called prime. So if they have exactly 2 factors, 1 and the number itself, then these are called prime numbers. That's what it means to be prime. Composite numbers will have more than 2 factors, like 4, 6, 8, 9, and so forth. Those are composite. We have one number that doesn't fit anywhere. Okay. 1 only has a single factor. So it doesn't fit the definition for prime, but it also does not fit the definition for composite. So 1 is a special number that is neither prime nor composite, which we'll see in the next definition. So any non-zero whole number with exactly 2 factors is called a prime number. Non-zero whole numbers with more than 2 factors are called composite numbers, so we saw that. And since 1 only has a single factor, it is classified as neither prime nor composite. Now, the thing about prime numbers is we have to test for them, because there's no end to them. They keep on growing and growing, okay, but nobody knows a pattern for their growth. So just to show you, for a long time, up until 1951, from 1876 up to 1951, this was the largest known prime number, because people had to test all these things by hand. And then, of course, computers came along. And now, here's a representation of the largest known prime number we have. Okay, that's not as written out. We can't write it out because it's 17 million, more than 17 million digits long. Okay, so we wouldn't have room to fit it on here, and it would just take forever to write. So this is the closest thing we can represent it. Now, every prime cannot be represented this way. But we know that this is currently the biggest one, but now they're getting so big that it even takes a computer forever to pump out the next prime number. So one of the things you had to do for your basic skills test is determine if a number is prime. So we can use certain divisibility tests to tell us if there are certain factors that will go into a number. Okay, so all we have to do is try to test prime numbers up to the square root of that number and see if they will divide into that number. Since we test 2, we don't have to test any multiple of 2. That's nice. And then once we test 3, we don't have to test any multiple of 3. So we only have to test the prime numbers. Okay. So since I don't have to test for 4 because 2 goes into 4, so I already know that if 4 goes into the number, 2 goes into it also. So here are some prime number tests we can look at. So let's look at 53. Okay. So if we go by some divisibility tests, we check 2, we check 3, we check 5, we know that they don't go into 53. And if we check 7, it also doesn't go into 53. Okay. I don't need to go higher than that because the next prime number would be 11. And 11 squared is 121, which is great deal more than 53. So I don't have to go any higher than 7. Okay. And I can show that I can't build any rectangles with these dimensions, that I only use 53 tiles to make. Now, I said we didn't have to go test the next prime number, which is 11. But if we even tried to test the next composite number, which is 8, 8 times 8 is 64. That's still bigger than 53, so we don't have to test anything bigger than 7. So this is our test written in formal symbolic notation. So if we look at n, suppose n some whole number, and k is the smallest whole number, such that if I square k, I get a number greater than n. If there is no prime number less than k that is a factor of n, then n is a prime number. Okay? So, if I am looking at some number, say like 53, like we just looked at, I want to see, can I take some number k that k times k is greater than 53? Well, we just saw 8 times 8 is 64. So what it says is that I do not have to test prime numbers bigger than 8. I don't have to test prime numbers bigger than 8. And if none of those numbers that are less than 8 go into 53, then 53 itself is prime.